Welcome to the ceremony award for the ADIA Lab Market Prediction Competition. First, I want to thank our partner for trusting us in building this competition together. We've learned a lot, and I hope you also learned a lot. We had a great success of participation, so thank you for the participation. We had 6,000 code submission in 3 months, which is amazing in terms of quantity. But we also had an amazing quality. And obviously, you will see from the 10 people who won that we will reveal at the end, the quality of the people is amazing. People are really talented. And not only they are good in terms of scoring, but are also very good in terms of originality of the solution they brought together. We are very pleased to be here at ADIA Lab, in the ADIA Lab offices, where CrunchDAO came with the team. Everybody is here with me. And for those who know, we actually relocated the team from Paris to Abu Dhabi, where we have actually offices in another floor in this building. And we will be working out of Abu Dhabi for the following future. So the ceremony will have 4 parts. The first one, Benjamin will present a quick introduction of what we do at CrunchDAO. You probably all know Benjamin. He has been really instrumental in building the community with ADIA Lab. He has been interviewing people who come to the platform, most of the people who come to the platform. He has been preparing and presenting the AMA, and also he has been organizing quant clubs. So we invite people who are actually close to these quant clubs to join. It's a physical event, and we will talk a little bit more about it. The second part, we will have a panel with Professor Marcos Lopez de Prado and Dr. Horst Simon, which will be presented by Matteo Monzi, our lead quant, and it will be about replicability in AI and p-hacking and implication in quantitative finance. So that will be very interesting. And the last part, we will dig into the data analysis of the tournaments. So this is something that you don't see in most competitions. So we will really take you to the backstage and see what we really see in terms of performance of participants. That will be presented by my co-founder, Jean. And the last part, obviously, the ceremony award where we will reveal the 10 winners. But we will present the profile, and you will see the people are highly talented people. And then we will also present the certificate that ADIA Lab will propose, will give to some of the best people in terms of robustness and stability of the model. Because not only the performance is important, but also the stability. So let me introduce Benjamin, who will present CrunchDAO. Thank you very much.
Thank you very much, Arnaud. Thank you. Well, thank you very much for being with us today from Abu Dhabi. And now I guess we will talk a bit from CrunchDAO. So a very short presentation on what is CrunchDAO. CrunchDAO, it's a bridge between quantitative machine learning specialists, researchers, and institutions. So when we talk about this bridge, what do we mean? Well, first, it's a community of 5,000 people that are actually coming from more than 91 countries. We have 600 PhDs with us. And so basically it's people coming from several backgrounds like mathematics, computer science, astrodynamics, statistical mechanics, fluid dynamics, theoretical physics, biology, and computational chemistry. We were able to double the size of the community in the last 6 months. And talking about this community, when we say it's about 5,000 people, what does that mean? Well, it's 50% that are coming actually from Asia, 30% from Europe, around 15% from America, and then Africa, and of course, Oceania. So, what is this bridge? Well, and why? Well, from one side, you have institutions that can't share their data. And from the other side, you have researchers that don't want to share their IP. So CrunchDAO is the secured middleman between institutions from one side and researchers from the other side. But CrunchDAO, it's not just a community, online community. It's also physical communities. And we were able to launch several quant clubs in the last 3 months. Basically, we have more than 700 quants that joined the quant club, the local quant clubs. So we had initiatives in Paris, New York, London, Singapore, Bandung, Abu Dhabi. Actually, Abu Dhabi and Singapore and Bandung will be launched next, but we already have had 3 events in Paris, in London, and in Bangalore. So I would like to take this opportunity also to say thank you to the people that are coordinating on the ground. Especially, I'm thinking about Amir Rezae, which is a very high-skilled researcher, Christian Caillot, Amit Nandi from Bangalore, Tero Likala in London, organizing the Quant Club of London, and Siti Khotija, that is actually doing a PhD on causal inference, by the way. And also, it's a good opportunity for us to thank the network of universities that are trusting us, that are helping us and supporting us every day. I'm thinking about HEC, Dauphine, and Duke University. That's it for the short CrunchDAO presentation, and I will give the mic to Jean, that will now explain why this bridge, why we, actually it's more Matteo Manzi, sorry, why we built this bridge together. And yes, welcome, Matteo.
Yeah, thank you, everyone. Thank you. I'll try to give you a walk through the reasoning behind the need for not only crowdsourcing financial machine learning, but also the need in general for highly parameterized models in the field we are working in. So I would like to start thinking about the common points between these 3 pictures. So we see a picture of the climate. Another picture is the price action of a stock. And finally, we have an avalanche. So these 3 are 3 examples coming from apparently different fields, but they're all complex systems. So these systems are time-dependent systems that evolve following a chaotic nature, but not only this, the nature is such that because of the high dimensionality, there is an evolution that leads to emergent properties and evolutions that are not explainable by the individual particles, building this ensemble of complexity. I wanted to highlight the history that led to complex systems, going from Poincaré and the study of chaos theory, with Ilya Prigozhin on dissipative structures, and finally Mandelbrot, of course, the father of complexity in financial markets. With this, I would like to arrive at the point in which it's clear that it's necessary to have nonlinear descriptors of these systems. In fact, this is a trivial example, but you can have in a univariate relationship structure, you can have obvious patterns. I'm looking at the last row here, in which using linear lenses, it's impossible to detect something. However, using nonlinear tools, it's possible to have these structures emerge. And this can be seen actually in a financial data set that we worked on. And just looking at the covariance matrix, basically, so linear tools, looking at the gram matrix of the simple dot product, there is no structure, no apparent structures, but as soon as we impose a nonlinear kernel, so a nonlinear measure on top of this point of clouds of point, then a structure emerges. So this is one of the reasons for which it's important to tackle these problems from the perspective of machine learning. And as clearly outlined in the past, while it's important, it can do more harm than good if not used properly, because there are more ways to be wrong than right, let's say, compared to easy and low parameterized models. Moreover, and let me continue on this, there is a need for developing tasks that and tools that are not trivial. And finally, alpha decay, this characterizes both low parameterized and highly parameterized models. because of alpha decay and strategy crowdness, it's important to constantly improve. And maybe we will try to back this statement up in the following part of the presentation. So let's go through the ingredients that characterize the interesting, let's say, perspective to look at this complex system, and then try to argue as of why it's important to have a crowdsourcing machine learning endeavor. So, of course, overfitting, because of the low signal-to-noise ratio, as I said, a highly parameterized model can easily grasp the structure of noise and perform poorly out of sample. Moreover, next slide, please. The non-stationarity. So we have a number of ways in which the relationships are explicitly time-dependent. This can be the structure of the noise, so heteroscedasity, seasonality, obviously, but most importantly, concept drift, which leads to deep variation of the structure of the data-generating processes. Moreover, fat tails, so the issue, and I wanted to highlight, again, Mendel brought with the introduction of fractional calculus and Levy distributions to characterize financial markets, that suggests us that while it's easy to put on the lenses of Gaussianity, it's not in agreement with observations. So financial markets are characterized by the possibility of still low probability, but possible, high risk events, and our tools should adapt to this fact. Finally, non-Markovianity. This again goes together with fractional calculus, but because of serial autocorrelations and memory effects in these data generating processes, it's important to adapt our tooling to take this into account, basically. Finally, I think this is the most, personally, the most interesting aspect is the low signal-to-noise ratio and the possibility to look at structures which are made of pure noise and then think of real observations as a superposition of pure noise and this low signal structure. So random matrix theory and the interest in looking at the spectrum of pure noise, high dimensional matrix emerges. And throughout I'm recommending some references that are really interesting. And then p-hacking and backtest overfitting. We mentioned overfitting, but here we are really talking about trying to have a perspective in which the scientist, the researcher, is actually part of the experiment environment. And so it's important to model his interactions with the data generating process in front of his work. And so say something about the stochastic process of his experimentation, his or her experimentation. So another thing that we try to think about when we work in crowdsourcing financial machine learning is the fact of, let's say, the necessity of how works are performed in traditional financial institutions, the lack of collaboration, which is necessary to have competition, but that leads to some inefficiencies. And together with this, the difficulty of leveraging collective expertise. Again, we'll try to stress the importance of this in the following slides. So I'll pass the ball to Jean for the next section.
Thank you very much, Matteo. So thank you so much for the reference as well. I guess there is many participants that could get some help from the few books that you have been putting into these slides. Some very interesting example. Now, facing these issues, we had to come with a solution. We had to find a framework to solve these issues in machine learning in this type of complex system. And at CrunchDAO, we have an approach that is, I may say, kind of game theory optimistic that also leverage collective intelligence. And to explain you again this because you all know people that are currently looking at us, I'm going to try to show you one experiment that has been conducted by Microsoft in early 2000 that is, I think, highlighting collective intelligence in a very interesting way. And this experience is called Kasparov versus the world. So in early 2000, Microsoft developed this collaborative chess game. This was one of the first games that you could play against other people around the world. And they had this very good idea of having Kasparov, like the title
said, it's played against 50,000 players around the world. And each player that was trying to compete against Kasparov could vote for the next optimal move and how to beat this genius of chess, which is still considered one of the greatest chess players in the world. And interesting fact about this game is that Kasparov said that he never played such an interesting game. It was so interesting for him that he actually wrote the longest book about a single chess game in the history of chess. It's 200 pages because he faces the most extraordinary and interesting moves that he never sees from a single player. And Matteo, you were mentioning alpha decay. You were mentioning strategic rawness and the fact that there is this constant need for innovation in finance, right? In this experiment, I guess we can really understand and have a grasp at how interesting is collective intelligence and how performant it could be. Because when you know chess a little bit, the difference of a player of the level of Kasparov and any grandmaster in the world is enormous. It's absolutely gigantesque. So you probably wonder about the outcome of this game. Well, Kasparov won. But fun fact, he actually cheated. It's a strong word, but he had access to the chat and he could see the discussion that the players were having during the vote of the next move. So they were basically arguing about moving this pawn, one or two move, you know. So he actually had an information that he was not supposed to have. So this game was declared a draw after that he revealed this information because he felt very humbled by the game and the beauty of the game that he found. So, I mean, for me, this is a beautiful experiment. Now, how can we use that and try to leverage the same type of techniques and use it in machine learning? Well, for example, in this graph, you can see that by combining different machine learning together that are completely different techniques, you could actually create a composite of this machine learning algorithm that could outperform any individual component of the crowd. Well, this is a very difficult exercise. It's not trivial, but this is an hypothetical outcome that we could reach if we were able to leverage in a very efficient way collective intelligence. Now, another fact that we had to face regarding alpha decay, strategic rawness, is the speed of innovation. Well, to find this new move, these interesting moves that was impressing and that almost probably would have beat Kasparov, you have to come with new idea, and so you have to innovate. When we look at the innovation path in artificial intelligence publication, and this graph is not up to date, because for the moment, this data has not been updated, but there were about 300,000 publications about AI every year that was published in the world. So it's close to impossible to follow this path and actually read all those papers. Well, some papers have more importance than others, obviously. The number of citation could actually help you understand what to read first, what was more impactful. But another interesting fact is that those papers were actually spread around the world, and you have countries that are publishing less, but that have papers that are very impactful. And so the other interesting fact about using a community to solve those complex systems is that you can access the outcome and the innovation of people that you would not have access if you were talking to the people that are in the same university as you or the same institution or the same research lab. And now that we had this, now that we have this concept in mind, I want to dive into the technical details of how we enable this collaboration. So how could we build this Microsoft software, Kasparov, against the world? Well, first thing, we are using differential privacy. Differential privacy is the fact that we will be obfuscating the name of the parameters, the name of the features, and the name of the assets that we have in our data. These techniques allow any third party to share data with the CrunchDAO without sharing the actual information inside the data. So when you work on a data set at CrunchDAO, you don't know what you are actually working on. And what is interesting is that you don't really care, actually. And this is another side effect of this, is that because you don't have to understand what are the features about, this allows a multidisciplinary approach to this problem. So you can have researchers from many different backgrounds, many different techniques, many different schools. For example, in chess, we used to have the Russian schools and other schools that had different approach to the game. By allowing this multidisciplinarity, you actually allow this diversity of approach. That's another very interesting fact. And finally, we avoid the ability to use bias, external bias, in your final decision. You really have to work with the numbers and with a quantitative approach. This image will show you a bit in a more graphic way what is happening. So this obfuscated data set is given as a flat file to our researchers, and you have this obfuscated information that can be treated by any researcher that has a data science background, which most of the researchers have, and that can be used to build a model and produce a predictive outcome. So insights, inferences, you can call it differently. Then the final step will be combining this forecast that has been created by all these players, right? We are again in this game, Kasparov versus the world, and you want to make the next optimal move to beat the master. So you will be combining these different forecasts. Those forecasts are trained on different moments of time, because with a machine learning model, you have these two steps. Maybe I should specify it. First, you train the model, and once trained, this model can produce a prediction. So people will make some choice and diverse choice, and this is where a lot of the beauty happens, because they may train on different parts of the data. They may use different labels to train their model, and they will use different techniques. And so once combined, on the next slide, Matteo, if you could, thank you so much. You can build, for example, an investment strategy. In the case of finance, if you want to build an interesting investment strategy, you will have to face about more than 40 years of research in the domain. And many of the relationship has been explained or are owned by some institutions. So you will have to come with some new idea and again, originality to beat the techniques that are already known. Again, the chess example works here. You have these classical games that have been played already. If you play these games, there is a solution and there is a best outcome, right? So you will have to come with what we call orthogonality. So orthogonality means the capacity of creating an outcome that doesn't explain something that is already explained. And at CrunchDAO, we have been building a command line interface that allows to integrate in the training of the machine learning models these common sources of return that has been explained in the past. Now, and I think this is how I will introduce the second part of this presentation, is the fact that these factors have been created along history for many different reasons. And we could argue that these factors have been explained in more or less efficient way. And we could actually argue that the way that the factor industry has been explaining the return is maybe not true. So there is two main effects that we will discuss. Is replicability of this research. So are we capable to replicate what they have been produced? And are these results p-act or not? And to explain this, I'm gonna give the floor in 5 minutes, I think, to leave it a bit the time to set up, to Professor Marco Lopez de Prado and Dr. Horst Simon, alongside Matteo Manzi.